let us continue our discussion of Newtonian mechanics with examples. In the last couple of weeks, the examples that we considered mostly we took examples in the situation where the objects were motionless in static condition. From today onwards, we are going to relax that condition and we are going to consider examples where the system under study can be motionless as well as they can be moving. So, we are going to consider the more broader application situations covering Newtonian mechanics. Today's topic is going to be friction. We are going to review critically about the basic concepts about friction. Now, why friction is important? It is important because remember from our earlier in the context of Newton's law, we said that it is very hard to appreciate Newton's first law of motion, because it is very hard to imagine or realize in everyday life a situation which is completely force free. And two forces that are almost always present in any real life situations, one of them is the gravity, the interaction with the earth, and the other force is friction. So, our plan is the following. So, first we are going to look at friction in two different situations. In the first situation, we will consider the friction between two solid interfaces, which we are going to call the dry friction. And then, so our plan is to critically review your so called Coulomb's law of friction that I am sure you must have already studied in your high school, but we will see there are some of the things that are usually not highlighted well enough. We are going to cover those aspects of the laws of about the friction force. After that, we are going to look at the little bit about the friction between a solid and a fluid, which is called a drag. Both of these situations are very common in various daily life scenarios as well as in various engineering applications. So, you should have a good conceptual understanding about the nature of these forces. First, let us ask this question: why is there a frictional force? And in this case, I am going to consider only situations where two solid surfaces are in contact with each other. So, let us take this simple example that I am put a book on a table. So, let us say imagine as before that this is my table and this is a book. So, I put a book on the table and let us say this book is at rest. Now, what are the forces on the book? So, we are going to consider the book as our system, then in the surrounding there is earth and the table, and there are forces, the gravitational forces on the book by the earth, which is this F grav, which is acting downwards through the center of mass of the book, and the force F table, which is upwards through the by the table on the book. Now, so this we have done before, we have drawn the free body diagram of this problem and applied Newton's third law, second law, etc., to analyze this situation. And we know that the book at rest means these two forces cancels each other. These are two distinct forces, but they happens to be equal and opposite because the book, we know that because the book is at rest. Today, let us try to look at the nature of the contact force by the table on the book. So, imagine if you could zoom in to the contact between. So, if this is your book and these are the contacts between so let us say these are the contacts between the book and the table, Now, if you could zoom in or look at only at the contact areas, let us say under a microscope or something, then perhaps you would get a picture like the following. So, what it is showing in this picture is that the green balls are the idealized version of the atoms. So, this table is a solid object, and to a very idealized picture, we can imagine this table as made up of atoms, the components of the table whatever atoms like a green balls, and these are placed in regular positions in a periodic positions that makes the table. Let us say this is a metallic table and or a wrought iron table, and there are forces between these atoms which are represented by these little springs. So, the atoms are connected by springs to represent that they can exert forces on each other, and on the top of that, if two atoms comes close to each other, so there is a equilibrium distance, a preferred separation between two atoms when represented by the fact that the spring is unstretched. Then if the two atoms come closer to that separation, then they will try to repel each other, and if they go away from each other, then they will come back to this equilibrium unstretched position of the spring. So, this sort of qualitatively describe the force between the two atoms in a real solid material, but note that this is a very idealistic version. This spring does not represent the actual force, it is just a crude way to imagine the atomic scale, how the table will look like under atomic scale resolution. So, what we will see here, which is important, is that we will see that because of this book, there is a deformation in the surface of the table. So, that is what is important, that there will be a deformation at the atomic scale of the surface. So, and this deformation, so the table is trying to remove this deformation, and hence it is producing a force on the book to push it away from the table. Now, let us ask this question: what happens if I apply a force on the sideways direction? Well, here is a schematic picture of that. So, if I put a force like shown by this red arrow on the sideways position on the book, then there will be further distortion on these atomic arrangements of the table. And it is easy to see that because of these new distortions, new kinds of deformations, now the force by the table on the book will have a horizontal component, because it will also try to remove the distortion or deformation in the sideways direction. And so, the contact force now has two components. So, to contrast, in the previous case, when the book is simply at rest without any external force, the contact force has only a normal component which is normal to the surface of the table. Now, in this case, because the nature of deformation is now different, it has an horizontal component as well as a normal component. So, this horizontal component, so the net resultant contact force is no longer perpendicular, let us call that contact force Fn or n, and the horizontal force, and as you can expect that the horizontal force will be in a direction to remove this deformation, and hence it should be in the direction opposite to the applied force. So, it should be on the left if the applied force is towards right, and this horizontal force is called friction, as simple as that. So, a contact force in general between two solid surfaces in contact, the contact force has two components, one which is perpendicular to the surface of contact, second which is horizontal to the surface of contact. and by convention the normal force is called the normal component and the horizontal component is called the friction. So, this contact force in general has a component normal to the surface and a component parallel or tangential to the surface, and so this is what we know from experience, that this tangential component of this contact force is present if the two surfaces have a relative velocity, if they are trying to move past each other, which is causing this, which will cause the deformation in the contact area, or a tendency for relative velocity. So, it may happen that this is crucial, because it may happen that if I apply this force, some horizontal force on this book, but if my force is small enough, it is the book will not move, but it will have a tendency to move. So, this tendency is crucial, and so if there is a tendency for relative velocity or actual relative velocity, then this horizontal component is the friction. Now, note that in this picture, this is a very idealized version of the picture, and this is the picture is not complete, in the sense, even in nowadays there are a lot of questions that are whose answers are not known about the nature of the frictional force at the atomic scale resolution, and people are still doing research on this area. So, now some definitions. Static friction. So, when two surfaces have a tendency, but not the actual relative velocity, for relative velocity, and the word is crucial, that the velocity must be measured with respect to each other. So, it may happen that your the table and the book both are moving with let us say they are in a train, moving train. So, they are both moving in the same with same horizontal velocity if you are observing them standing on the road, but there is no relative velocity is 0. If the relative velocity is 0, then there will be no frictional force. This is crucial to remember. So, there is a relative velocity, but are not actually moving with respect to each other. So, with respect to each other is the crucial point. So, then they are still static, motionless with respect to each other. So, in this case, the effect of this there is still a horizontal force which is trying to prevent slipping of the contact between surfaces. So, think of these forces as something that is trying, so they are trying to slip past each other or slide past each other, and this force is trying to prevent that from happening. So, as I showed a little earlier, that this is an example whether you are pushing on a book on a table, but the book is not moving. So, it has a tendency to move, but this horizontal force is resisting the motion. Now, we come to the very important fact, what is the, how to describe, how much is the friction. So, here what you already know, got introduced in your high school course, is something called Coulomb's law for friction, or more precisely, more accurately, the Amonton-Coulomb law for contact force or friction. So, what is this law? So, I am going to highlight two important aspects of this law. So, as you know, it says that if n is the normal component and f is the frictional component, then this frictional force has what is the magnitude of this frictional force. So, this is the first part, that the magnitude of frictional force is not unique. It can have anything from 0, the magnitude, I am talking about the magnitude. It can be anything from 0 up to a maximum, and this maximum value of frictional force is given by the mu times n, where mu represents the coefficient of static friction. So, mu is a constant. So, and this mu can be any positive number. So, there are two important points that are normally missed as far as I noticed from students understanding, that you have to remember that the frictional force does not have a unique value, it varies from a range. So, it starts from 0 and it goes up to a maximum value, and this mu times n represents the maximum value of the friction. But there are situations, very common situation, we will consider these when we take some example, where the frictional force can be actually less than mu n. This is the first important point, that this is a inequality, it is not equality. The second point is that if I ask students what is the value of mu, I always get an answer that mu varies from 0 to 1. So, what is mu? Mu represents the ratio of the frictional component, the horizontal component, and the normal component of the force. Now, what does mu equal to 0 signifies? It basically means that we can ignore the frictional force compared to the normal force. So, it is like the surface between the two objects is frictionless or very slippery, like if you are walking on ice, ice is very slippery. So, the friction is very almost 0. So, this is if you sort of think of in a ideal case of an extremely slippery ice surface. So, that represents mu equal to 0 example. Now, if these two forces are equal in magnitude, then mu becomes 1. Now, can mu be greater than 1? The answer is yes. There is absolutely no restriction either from our experience or from experiments that the frictional component cannot be greater than 1. In fact, in the limiting case, it can be infinity, meaning it can be as large as possible. So, what do I mean by that? It is very easy to see. So, you also already so think of it as two surfaces which are glued to each other. So, there is a gum, we apply some gum to glue one surface to another surface, like you put some gum and close an envelope. So, this gum in that condition, because of the presence of this adhesive like a sellotape or something, the frictional force is extremely high, the horizontal component is extremely high. So, that represents a scenario in which mu can be very high. So, remember that there is no upper limit on mu, and it will lead to some surprise which we shall show you in the next lecture, even in a very familiar example. So, mu can be, there is no upper limit of mu has to be 1, it can be greater than 1. Now, I want to highlight one thing, that this friction force is then in principle unknown. The reason you always take F equal to mu n is then you have some expression for F, the friction, but in reality friction is a self adjustable force, which means its magnitude is not always known from the situation. This is a reality. Just so you cannot ignore the fact. This is also consistent with our experience, as we shall show in an example. Now, what about the direction? The direction of mu is given by the fact that it opposes the relative motion between surface. This comes from our physical picture, that this friction, the horizontal force, is that aspect of the contact force which is trying to remove this deformation. Hence, the direction is of the friction is given by the simple rule that it opposes the relative motion, or in this case the tendency of relative motion between surfaces, and that sets the direction of F, and usually the direction of F is clear from the situation of the problem that you are trying to solve. Now, the third important point about this Coulomb's law of friction is that it is an amazingly simple law. The ratio, it says that this ratio of the frictional force and the normal force, which is this coefficient mu s, it does not depend on the area of the contact. So, this is a very strange and very surprising aspect of this law, that we do not know actually this contact force in reality can be enormously complicated, and we really do not know those contact forces, but it just says that you do not need to know all the details of atomic level details of what is going on in the contact, just measure the normal component and the horizontal component, and their ratio is a constant, which means if you increase the normal component, the horizontal component will automatically increase. Although I should mention that these mu s do depend on the nature of the surface. So, the frictional force between a book and the wooden table and between the book and the wrought iron table are going to be different. For the completeness, I will also mention the sliding or the kinetic friction when two surfaces are actually sliding or slipping with respect to each other. For example, if the book is actually being dragged on a table, then the Coulomb's law says that if now the friction is given by again basically the same form, that this friction is proportional to the normal component, and the coefficient of proportionality is now called the coefficient of kinetic friction, and experimentally it turns out that this value is either equal to the coefficient of static friction or slightly less than that. So, again I emphasize that this simple formula, simple looking formula is easy to state, but it is actually very difficult to sort of give a first principle proof of or derivation of this formula, that why it is to be the case. So, all because this formula says that all complications about surfaces are represented by just a single number mu, nothing else, no contact area, no relative velocity, no dependence on contact area or the relative velocity in the case of kinetic friction. It is an amazingly simple law. So, to summarize, so I sort of reviewed the Coulomb's law of friction, and there are 3 points that I want to highlight or highlighted when I did the critical review. First is that the frictional force can be anything between 0, minimum value is 0 and maximum value is mu times n, and it is a self adjustable force, its magnitude can vary within this range. Second thing is that the direction is given by the tendency to oppose the relative motion or the actual relative motion in the case of kinetic friction, and the coefficient of friction mu, it can be any positive number between 0 to infinity. So, it does not have to be restricted from up to 1. And the third part is I want you to appreciate this simplicity of this law of Coulomb friction, that absolutely we do not have any idea about the nature of the contact force, what are the positions of these atoms, but still we can describe the frictional force without knowing anything about that. So, in the next lecture we are going to consider examples. Thank you.